Hello, we are Group 3 from BSCS2A. In this video, we will demonstrate our practical implementation, a random forest credit scoring system with SHAP Style explainability, built entirely from scratch in Python with no external machine learning libraries.
Now we will demonstrate by explaining the three algorithm implementation from the scratch. So here are the core mathematical utilities. The Gini function computes impurity using the formula 1 minus the sum of squared proportions. So this is O of k, effectively constant for binary classification. And the weighted Gini function combines two children's impurities weighted by their sizes. This is what each tree uses at every split to decide the best threshold. So here, the decision tree is built entirely by hand. The best split method scans every feature and every midpoint threshold. It computes weighted Gini for each candidate and keeps the best. So the build method is recursive. It grows the tree until it hits max depth, a minimum sample count, or a pure node. So the time complexity is O of n times d times log n. Space complexity is O of n times d, because every node stores split conditions. So here, so in the random forest contains 25 trees, and for each tree, bootstrap draws and sample with replacement. This is bagging. Then we randomly select square root of the features. This reduces correlation between trees. So each tree is trained on its projected bootstrap sample. So total complexity is O of t times n times d times log n. And the trees are independent, so in production they can be parallelized. For the function of SHAP explain method, we aggregate feature importances across all 25 trees. The SHAP explain method then computes a assigned contribution for each feature important times the deviation of the feature value from the neutral point of 0.5, and for the features where lower is better, like the ratio, the sign is flipped so that a positive contribution always means the feature pushed towards approval. This directly satisfies the GDPR and ECOA.
By the way, this is our code, and let's run the code. So as we can see, we have the generating dataset. So we see the 200 records with 164 training and 44 testing. 106 applicants were approved and 94 were rejected. A roughly balanced dataset, which means our model will not be biased toward one class. Next, we have the training random forest rather. So the training random forest achieves 98.8 accuracy with perfect recall, and this is expected, and it proves that algorithm is correctly fitting the training patterns. The high F1 scores confirms that model is not ignoring the minority class. So next, we have the test set evaluation. So test set evaluation accuracy drops to 77.5% on the held out test set. This gap between training and test accuracy is the bias variance trade-off we described in the analysis report. It is normal and expected. So the 79.1 F1 score on unsent data confirms that model generalizes well. So next, we have the global features importances. So global SHAP importances, we have the income level, debt ratio, loan amount, payment delays, credit history. So this matches our critical expectation. Macro financial capacity features carry more weight than historical payment behavior. Any loan officer can read this chart and understand the model priorities. And last, we have the individual applicant decision. So the individual applicant is scoring. Applicant A has strong features and receives 84%. So probability approved. Every SHAP contribute is positive, meaning every feature help. So the applicant B is have 28% probability rejected. So every contribution is negative. And lastly, we have the applicant C, which is borderline. So at 48%, just below the threshold. So the near zero SHAP values confirms that model is genuinely uncertain, which is the correct behavior for our borderline case. That's all. Thank you.
Our analysis report predicted that the random forest algorithm will achieve the highest accuracy among the three algorithms. The 98.8% training accuracy and 77.5% test accuracy confirm this. The test drop is also predicted. The report explicitly notes that the random forest algorithm requires post-havoc explainable AI tools because it trades interpretability for accuracy, which is exactly the trade-off we observe. The SHAP explanation for applicant B shows loan amount as the biggest negative factor. The features value is 0.85, extremely high, meaning this person is requesting far more loan than their profile justifies. This is actionable, human-readable explanation that satisfies GDPR's right explanation and ECOA's adverse action notice requirements. For the complexity defense, random forest training is O of t times times n times d times log n, and storage is O of t times n times d, with t equal to 25 trees, n equal to 200 samples, d equals to 5 features, and roughly 3 levels of log. Training takes about 75,000 operations, and storage is proportional to 25,000 units. This is manageable on the laptop but would require parallelization of the millions of applicant scale described in the report.